Hello, everyone, and welcome to the Rambus Design Summit. This is session number 4, and I am Tim Messagey. During this session, we are very proud to have Rambus Fellow and Distinguished Inventor, Dr. Stephen Wu, give our keynote presentation. If you have any questions for Steve, either during or after the presentation, please press the Q&A button at the bottom of your console, and Steve can address those questions during the Q&A session that follows. And with that bit of housekeeping out of the way, let's turn it over to our keynote presenter. Over to you, Steve.
Thank you, Tim. Hi, everyone. My name's Steve Wu, and today I'm going to be talking about how bandwidth is key to unlocking greater AI performance. Well, we've seen that AI is having a broad impact in the semiconductor industry, and especially in the area of chip design, we're seeing tremendous innovation in domain-specific architectures that are designed specifically for AI processing. But it's kind of interesting to take a look back and understand how we got to this point in the first place. It turns out that AI and many of the techniques that are implemented today have been around for decades. In fact, many of the fundamental methods that are used to train and implement neural networks and AI chips have been around since the 1980s and early 1990s. But they never really took off in that time frame. And the reason why was because processing capabilities and memory system capabilities were not quite as good as they are today. Now, if we fast forward a few decades to where we are today, the fact that we have compute that's about 5 orders of magnitude better than it was back in the 1980s and early 1990s, and memory systems that have higher capacity and better performance by about 3 to 4 orders of magnitude, being better than they were in that time frame, we're now seeing that the methods that were used with other conventional approaches no longer can match the performance of neural networks and AI. And the other half of the coin here is that we're seeing a tremendous growth in the amount of the world's digital data. And you see that on the right here. And we see this exponential growth where even by the most conservative estimates, the world's digital data is doubling every about 2 to 2.5 years. And so one of the things you need to make neural networks perform very well is lots of data that you can use to train them on. And it turns out that with this explosion of data, it's also enabled neural networks to outperform the more conventional approaches that were used decades ago. In fact, it's gotten to the point now where there's so much data in the world, you almost need AI and ML techniques just to make sense of it all. So from that standpoint, you're getting this kind of virtuous cycle where the larger amount of data is used to train and make better neural networks, and the neural networks are able to sift through this data and make sense of it all. Now, the more interesting thing that's going on is that we are still in the early days of this generation of AI work. And so there's a tremendous need for more performance and for better solutions. But the real irony of it all is that at this time when Moore's law is really slowing down and ending, and power efficiency and power scaling has all but ended, how is it that we can continue to provide better performance and better power efficiency when a couple of the tools that we've relied on for decades, Moore's law and Dennard scaling, are really slowing down or no longer available to us in the future? Well, if we take a look at what some of the critical elements are in our AI systems, you don't really have to go very far to realize that one of the key bottlenecks in AI today is the memory system and memory system performance. There's a lot of different articles and studies and things that point to the fact that memory systems can be a key limiter. And so here's just a few examples of the many kinds of articles where people have looked at this particular limiter. And so I'm going to talk a little bit more today, not only about the limitations that are imposed by memory performance, but also some of the things that happen when you don't have enough link performance as well. So more specifically, if we take a look at some of the limitations of memory, one of the really interesting things that's going on is that AI models themselves, and of course the training sets that are used to train those models, are growing dramatically in size. And what you see here is a quote from Naveen Rao, who back late last year was talking about Intel's AI work that they were doing. And one of the things he pointed out was that the neural network models themselves are growing on the order of 10x per year, and basically growing faster than any other technology curve out there. And so it was causing kind of a big issue that the capacity needed to store these models was a big deal. And it turns out that along with that, of course, are the training sets as well. And so the data was growing exponentially too. And so this places tremendous demands on the memory system. And you can see how the memory system can become a bottleneck, moving the models and all that data onto the chip so that it could be used for training and to update the models, and even to process using inference was causing issues. And so memory systems are definitely a big bottleneck. In fact, a little bit more information is that earlier this year, the actual largest models were on the order of about 15 billion parameters. And just in June, OpenAI released their newest speech model, GPT-3, and it went to 175 billion parameters. And so now we're seeing really trillion parameter models are on the horizon. So there's definitely a desire and a demand for better accuracy and bigger models. Now, the way that the industry has responded is there's a lot of interesting techniques that have helped stretch the resources that are available. Things like reduced precision mathematics, quantization, and even sparsity help make much better use of memory bandwidth and the available compute resources by either eliminating computations that are of little consequence or really minimizing their impact and really stretching the amount of memory bandwidth that you have to cover more computations. But what we're also seeing is we're seeing a tremendous demand for more memory bandwidth and higher link performance. In fact, in the case of memory performance, the highest memory bandwidth standards, GDDR and HBM, we're seeing them evolve at a rate that's faster than we've seen over the last several years. And so this speaks to the demand that we're seeing for more memory bandwidth in particular, especially for AI solutions. This slide here is from a paper that Google published a few years ago, and it was one of the first papers where they discussed their first generation tensor processing unit. And it told an interesting story about the importance of memory bandwidth. What they did in that study is they compared three different architectures, going from something that was more general, the Intel Haswell CPU, to something a little bit more specific, NVIDIA's K80 architecture, and finally to something that was purpose-built for doing machine learning and AI inference, and that was the TPU version 1. Each of those architectures has a solid line here called a roof line. And what the roof line defines for you is times when your architecture is limited more by memory bandwidth, and that's the sloped part of the line, and times when it's limited more by the compute capability or how many compute engines you have. And that's the horizontal part of the line. Now, for each of these architectures, what they did was they took a look at 6 different types of neural networks, and they coded them especially for those individual architectures. The stars represent the 6 different neural networks executing on the Google TPU. The triangles were for the NVIDIA K80, and then the circles were for the much more general Intel Haswell. And when the individual applications or those symbols, when they lay close to the sloped part of the roofline curve, it means on that architecture, that application was limited more by memory bandwidth. And when those applications lay closer to the horizontal part of the curve, it means they were limited much more by lack of compute capability. What you can actually see is that as you move from the more general kinds of processors, Intel's Haswell, and to something a little more specific, the NVIDIA K80, and finally to something that was purpose-built for AI, the Google TPU, you can actually see the Google TPU, the stars are, many of them lie right on the line here, the horizontal, or the sloped part of the line, which means that they're limited by memory bandwidth. And even for some of these other applications that are kind of near this corner point here, they're getting close to being limited by memory bandwidth as well. And so this was an interesting study that kind of pointed to the importance of memory bandwidth. And after this, what we saw was a lot of architectures actually using the highest bandwidth memories, because this became a realization across the industry. So it's very clear here that memory bandwidth is important for many kinds of neural networks and machine learning applications, and it will be this way into the future. So this slide here is kind of a well-known slide, and it actually shows the progression of improvement in AI training capability really over the last about 10 years. And what it shows is that there's been a tremendous increase in AI training capability. It's grown at a factor about 300,000, which means it doubles about every 3.5 months. And if you think about it in context of Moore's law, that's 25,000 times higher than the Moore's law improvement over the same time. And a lot of that improvement is coming from the fact that we're using domain-specific silicon it's purpose built for AI and machine learning, like Google's TPU, but also from the fact that we're able to now take some of our largest AI training jobs and split them among multiple engines and to get some parallelism. So the question is, there's certainly no shortage of demand for even more performance, and we would like to stay on this improvement curve, or even to do better than it if we possibly can. And as the point that I brought up earlier in the talk is, how will we continue to do this when two of the tools that we've relied on for so long are really slowing or no longer available to us? And that's really a key question. And I think it's very clear that we're going to have to continue using parallelism, and we're going to have to also continue with architectural innovations that help lead to new types of advances. So I want to talk about one of the interesting impacts of parallelism and the use of multiple engines, and sort of what it ends up causing as bottlenecks in the architecture. So on this slide here on the left, what I'm showing is a pretty simple scenario where I'm training a neural network to process some data set. And so the data set is shown on the left there, and there's a neural network that's embedded all in one chip. And so the conventional way to do this is to take all of our training data and to slowly cycle it through the chip, iteration by iteration, and I just make updates to the model until it becomes very good at classifying or identifying or processing the data in the way that I want it to, right? And so in this particular case, what really matters here is, memory bandwidth is an important part of the equation. Being able to push that data that's in the training set from memory directly through the chip. And so in many cases, the amount of memory bandwidth you have is a limiter, both in terms of the training time and the amount of energy you're going to spend in that training. But what a lot of people have been doing these days is data parallelism, and the idea here is that you take multiple training engines, multiple chips, and you split the training set among those chips. And so each one of the chips has a complete copy of the same neural network model. But what you do is you spread the training among those four chips. And so the idea here is that you can get some better improvement because now each of these engines is doing 1/4 of the training work. And you ought to be able to get some improvement in performance. Now, that's definitely true. The training task itself of updating the model does get faster because there's multiple engines doing a fraction of the training set, a different fraction, in parallel. But there is an interesting consequence to all of this, and I'll show you what that consequence is in the next slide. So when we're doing this type of data parallelism, we actually take each of our training steps and we break them into two phases. In the first phase, each of the training engines in parallel will update their own copy of the model with their fraction of the training set. And so each of the four chips here, at the end of running through their one iteration of their training set, they'll all have different updates because they've all seen different training data. And in this particular case, you're really, again, limited by memory bandwidth. It's how quickly you can get that training set into the chip to make your updates. But what you need to do now is you need to resolve the differences between each of these models, and the chips have to communicate back and forth and let each other know what updates they made. And what each chip has to do is receive the updates from the other chips, and then they have to collate these updates and then update their own model. And what you get in as a result is each of the models can then get back in sync with each other, and they'll all once again have the same copy of the model because they've all taken into account each other's updates. Now, what's interesting in this second phase, which is called reduction, is it's really limited more by the communication link speed between the chips. And so in the first case, in the first phase, where we were limited in many ways by the memory bandwidth available in the system, in this second phase, we're actually limited more by the link performance and the link bandwidth. And so in this way, you can see that the bandwidth of the IOs, both the memory subsystem and the chip-to-chip or the link performance, those are both key limiters in terms of training in the data center. And so in this way, bandwidth affects each of the phases a little bit differently, but they're both important limiters to what goes on. And that will continue to be true as we use more parallelism in the future. So the key here is that it's really important to balance both of these phases. You don't really want one phase bottlenecking the other phase, and you want to make sure that the amount of bandwidth you can provide, both in terms of memory bandwidth and the chip-to-chip or link bandwidth, is high enough that the training can proceed very quickly and in a good power-efficient way. So again, memory and links will continue to be critical as we go forward in data centers. Well, so what are the challenges with this? I mean, if we know that what we need to do is to provide more memory bandwidth and more link performance, then it seems relatively straightforward what we need to do. And so this slide here is actually a really interesting slide, which shows how difficult it really is to improve things like memory performance, and in this case, network latency, but it's similar to what you would see in links. What you can actually see is over the period from 1990 to this year, projected to this year at the time this chart came out, it actually shows that the rate of improvement of performance of the compute engines as measured in flops was actually outpacing the rate of improvement of memory and links in terms of both bandwidth and latency. And so just as an example, if you look at this purple curve here, what it shows is that the rate of improvement of compute as measured in flops relative to memory latency, the compute capability was getting better, was improving faster than the memory latency by more than 100 times every 10 years. So what that means is every decade you're waiting longer and longer for from the compute engine's point of view to actually get the data that they're looking for. And if you think about it in terms of memory bandwidth, it is a little bit better. The difference is here that the compute is really growing about 4.5 times faster per decade compared to memory bandwidth. So it's not falling behind as quickly. But the upshot of it is falling behind. And so, if you take a look at network latency and network bandwidth, those are good proxies for what you'll see in links as well between the chips. And so you see that, again, we're falling behind every decade. So if these things are bottlenecks today, they're only going to be worse in the future if we stay on these curves. So the challenge really is, how do we kind of fight against these historical trends and try and improve the performance of both memory and networks? And it's something that the industry continues to struggle with, but there are some really interesting innovations that people are working on that may help to try and stay level with where we are today, and hopefully to try and improve the situation as well. And so some of the things that have been done, especially in AI and machine learning, are to develop some of these new architectures and more domain-specific silicon, where we try and put more of the data on chip directly to get the benefits of being of higher bandwidth and better power efficiency and lower latency. But what we still find is that the data sets are often too large and that you do need memory. And so the goal here is to try to go more often to the on-chip memory if you can, but there's definitely still a need for the off-chip memory and for those links. So if we take a look at some common memory systems for AI and machine learning, the three most popular kinds of memory systems are shown here. There's definitely on-chip memory is, again, something that people try and make a lot of use of. It's great. You can get incredible amounts of bandwidth and very low latencies. You can get on the order of tens of terabytes a second of memory bandwidth, by far more than you can get with any external DRAMs. The problem is that you really have limited capacity. And so if you're talking about a single reticle-sized processing engine, you're on the order of a few hundred megabytes of capacity of on-chip SRAM, and it is kind of what is more state-of-the-art today. You can increase that by doing things like going beyond a single reticle size. So Cerebras has done that with their wafer scale engine. But even so, with their wafer scale engine, from a capacity standpoint, it's actually still less than what you would get with a few external DRAMs. And so you have to be willing to tolerate the lower capacity of the on-chip memory. And if you can do that, it's a great solution for you. It really is. But for a lot of applications, the capacity is so high that you need external DRAM. And on the right here and in the center, I'm showing the two most popular types of external DRAMs. In the center is HBM, which you've heard about earlier today, and GDDR, which you've also heard about earlier today. HBM is very popular. It's used in a number of the highest performance engines that we see, like the solutions from NVIDIA, and even in graphics cards from people like AMD. What's different about it is that it relies on stacking and a slightly more complicated overall system design that uses an interposer to etch a large number of very finely spaced wires that can connect the processor to the HBM devices. And so by having a large number of wires to each HBM device, I can have a very wide data path, and it doesn't need to run as fast. So it's low latency and very good power efficiency. It also relies on a new type of design for the DRAM devices themselves. So the DRAM devices are not a monolithic piece of silicon. They're actually a stack of silicon devices. Many of the silicon devices in that stack are actually DRAM layers, and they hold the DRAM bits. And then at the bottom of that stack is a base layer that provides electrical interface back to the processor through that interposer. I'll show you a little bit more in a minute about what some of those implications look like. On the right is GDDR memory, and that's another really popular solution for things in the data center for AI. And so with GDDR, what's interesting about it is it follows the more traditional kind of manufacturing flow. It is a monolithic piece of silicon that's packaged in a more traditional way, and that device is placed down directly onto a PCB. You do see this in some solutions like NVIDIA has the T4 solution, and there's, of course, lots of different graphics cards that use GDDR. GDDR has evolved several generations since it was first introduced around the year 2000. And so the latest versions of GDDR, GDDR6, are used in some AI and ML solutions. What they provide is a really nice trade-off between the bandwidth and power efficiency, as well as the cost and manufacturing difficulty and reliability. In the case of HBM, you get better performance and better power efficiency, but it is more costly to implement, and it does take more engineering skill to implement it as well. And so it is a trade-off. If you can tolerate that cost and you have the ability to design with HBM, it's a good solution. But if it's really not in the right range for you, then GDDR is a great solution as well. So I wanted to show a little bit more about what goes on inside systems that actually use HBM and GDDR, just so you could understand some of the trade-offs a little bit better. And so here, what I'm showing is just a graphics card that uses AMD's Vega 56 chip. And what you can see on the right, upper right there, is the actual processor and memory. So the large dark rectangle is the GPU, and these two smaller rectangles underneath are the HBM devices. And if we kind of turn it on its side and get a side view, you can actually see how all the components are placed so that the memories can talk to the processor. So the processor itself is connected to the HBM stacks through a silicon interposer. And there's circuits on the processor called a PHY, which are responsible for driving the electricals back and forth to this HBM stack. And of course, the HBM stack I mentioned has a die at the bottom, which has very similar functionality as the PHY here, which job it is to drive the electrical signals back to the processor. Now that silicon interposer, it turns out it can't be placed directly onto the PCB, so they mount it on a substrate, and that substrate then gets mounted onto the PCB. So lots of stacking is involved here. You get an extra substrate, extra interposer, and then of course in the DRAM device itself, there's extra stacking as well. It does lead to short connections, which gives you better performance and better power efficiency, but it is more complex and more costly. So, and they are newer manufacturing methods as well. But the difference here is that it allows us to have a very large number of wires, which means I can run them at a slower speed in order to push a lot of data back and forth. Now, if I were to actually take away some of the components of this card, I'll show you one of the issues which is coming up, which is power. And so as I take the cover of this card off, you can actually see here the thermal structure, the kind of the heat radiator with the heat pipes, whose job it is to move the heat away from the processor and the DRAMs and to move it over to where the fans are and to radiate that heat. It's a pretty large structure, and so things have been moving in this direction with more heat and more complexity in the thermal solution. And as I take that away, you can actually see the PCB where the actual GPU and the memories are right here. And you can see that the vast majority of the volume of that card is really dedicated towards dealing with the heat and the thermals. Now, if I compare that to a GDDR6 implementation, here's a GDDR6 graphics card. And once again, you see on the upper right, here's the graphics processing engine, and here's the packaged DRAMs. It's a much more conventional kind of assembly. And you can see below it, the processor is connected to the DRAMs directly through the PCB. There's no special interposer, no special stacking. So very familiar manufacturing processes. But the difference here is that you don't have quite as many wires going between the processor and the DRAM. In fact, you have a much smaller number. In this case, you only have 32 wires. And so it means to get the same kinds of bandwidths or to get any high bandwidth at all, you have to run those wires at very high data rates. And in fact, GDDR runs them at the highest data rates of any external memory in the industry today. And so the challenge here is maintaining good signal integrity and dealing with the extra power of running at the higher data rates. And so if we do the same kind of thing here and take away the elements of the graphics card, you can actually see once again, there's a really large structure here for dealing with the heat and radiating it through some heat pipes and fans. And if I pull that away, you can actually see the card assembly a little bit bigger. But again, the vast majority of the volume of that card is in that heat sink and the radiator structure. So obviously power is becoming much more of an issue, and it will continue to be an issue going forward. All right, so now if we just kind of compare the trade-offs between GDDR and HBM, what I'm showing here is if we wanted to construct a memory system that was that delivered 256 gigabytes a second, there's a couple different ways I could do that. I could do it with GDDR or HBM. In this case, GDDR6, I would need 4 DRAMs hooked to my SoC. And in the case of HBM2, I would need a single device. And HBM2, it's got a lot of data wires. In fact, it's got 1,024 data wires going between the SoC and the DRAM, which means if I want to get to that target data rate, I only need to run the wires at 2 gigabits per second. But in the case of GDDR6, if I want to get to that same performance level, I've got to run each of the data wires. It's a total of 128 data wires, basically 32 for each of the devices. I have to run them much faster at 16 gigabits per second. And it has some interesting consequences. So they're shown in this table here. The amount of area you need for the silicon of the PHYs, which are the circuits responsible for talking to the DRAMs, it ends up being bigger in aggregate for GDDR6 compared to HBM2. It's about anywhere from 50% to 75% more area for the PHYs on that SoC. So that's one consideration. The other thing that you see is that it's a lot more power. So across the 4 PHYs in total, it's anywhere from 3.5 to 4.5 times more power for the PHY compared to an HBM2 PHY. So these are big advantages for HBM2. But the other things that you have to consider are there are additional costs with using HBM2. So for example, the interposer and the substrate that I mentioned before, that's added cost. And of course, there's stacking in the memory itself, which is added cost as well. And so from that perspective, it really is a trade-off, and it depends a lot on what your system can tolerate. And there are definitely times when each solution is much better than the other, and it depends a lot on the constraints that you're facing. All right. So as we look forward, one of the interesting questions is, what has to happen in order to continue providing better performance, and how will AI start driving what happens in terms of memory and links? Well, if you actually look back across the decades, it turns out that the use cases were really the things which drove the memory industry and the development of new technologies. In the 1990s, as personal computing was taking off, and there started to be new productivity applications like Word, Excel, and PowerPoint, and they started to become ubiquitous. Things like synchronous memory were developed to really try and provide much more memory performance to support those applications. In the 2000s, things became much more graphical. Gaming started taking off, and game consoles were becoming very popular. And so a new type of memory, GDDR memory, was born that could really provide the levels of performance that the more mainstream memories could not. And then in the 2010s, what started happening was we started looking at new types of computing models, and we looked at things like mobility and things like having personal devices like phones. And so battery operated devices became much more important, which meant that power and mobility were very important as well. And so we saw a new type of memory arise here, which was mobile memory, LPDDR, for example. And what we see going into this decade is that really one of the key drivers is AI and machine learning. And we see that what's really needed is ultra high bandwidth and very good power efficiency. And we're seeing already that the impact and the demand from AI is changing roadmaps, and it's causing an acceleration in how these technologies are evolving. And we expect that to continue in the future. Now, one of the key challenges that I mentioned already is power and energy efficiency. And so this slide here is a kind of well-known chart, but it shows, it sort of speaks to the importance of the energy required to move data, around to the processing engines. At the bottom here, it simply shows the energy that's required to add two numbers together. And the red part of the bar is the amount of energy to actually do that addition. And you can see it's only a small fraction of what's required to set everything up to do the addition. So there's some amount of energy spent to do the control and some amount of energy spent to access the operands that you're going to be adding together. Now, the interesting thing here is the 25 picojoules, which is shown in this breakdown. That's if your data happens to be on chip in a cache somewhere. If that data is off chip in DRAM somewhere, you're talking a couple of orders of magnitude more energy just to fetch your operands. And so really what that means is this bar extends far to the left, as far as the eye can see. And so really you're dominated at that point by data movement. And so one of the tenets of architecture design is you're really not wanting to move the data unless you have to. And so we're seeing that impact today in the way that architectures are designed. And architectures will continue to move in that direction of much more localized processing because there's really no other way to address the tremendous impact of moving data over long distances. It'll still be required, but the goal will be to continue to minimize the number of times you have to go off chip. And so also rethinking how we build those connections. There's a desire to move to shorter connections, and there is research work being done in stacking to try and minimize the length of those connections in the same way that the length of the connections is minimized in the HBM stack. There may be opportunities to stack memories and processors together to minimize the connections there as well and to save energy. And finally, as we think about running our DRAMs at faster data rates to provide our data in greater volumes over time to improve that bandwidth, it turns out that there's a growing number of effects that have to be taken into account as the speeds increase. And so this slide here on the left, we're showing just a partial list of the effects that you have to consider when you're building faster memories. And of course, there's an analogous kind of chart for when you're talking about chip-to-chip interfaces and links. But what it really shows is that as you go at faster and faster data rates, there's just more effects that you have to take into account. And so ensuring good signal integrity really means that you have to identify what those effects are and be able to model them all the way from the transmitter to the receiver in order to ensure good signal integrity. Now, if you're able to do those things well, then by the time you actually go build your system, and I'm showing in the middle here Rambus's GDDR6 PHY evaluation system, by the time you actually get to the point that you're building a system, if you've taken all these things into effect, you'll have some good results. And what I'm showing at the bottom of that middle section there is I'm showing the transmit I for our GDDR6 PHY, which is operating above the kind of the highest current data rate for GDDR6. And so we're showing it operating at 18 gigabits per second, and it's a very clean eye. And it's because we did a lot of modeling, really, and it relied on a lot of methodologies that we developed over time to really ensure that our models would be accurate. And then on the right here, what you see is that there's a lot of work in the industry about trying to figure out, it's more than just the silicon. You have to think about what's going on the board and the package. And Micron had a very nice tutorial a couple of years ago at DesignCon. And one of the things they pointed out was that the VIA stubs were starting to become an inhibitor in terms of performance. And so using some kind of known techniques, things like DFE and VIA back drilling, they were able to improve the performance and really open up the eyes. And you can see at the bottom right there, you can see the baseline eye when trying to operate at 16 gigabits per second. And then you can see just simple one-tap DFE along with VIA back drilling pretty dramatically opens up that eye. And so what it really spoke to was that there are some good known techniques that the industry has that will help continue to pave the way for a faster speed roadmap for signaling. But there's constantly a new set of challenges that the industry is going to face. And so part of the job of our industry is to try and figure out how to continue ramping up the bandwidths, both in terms of memory and links, and the power efficiency as well, to continue to deliver more performance for these AI engines and other applications. So this brings me to the end of my talk, and I'll summarize very briefly here that, again, AI is having a broad impact on the semiconductor industry. It's really rapidly changing the way we consume and process information, and it's leading to lots of interesting opportunities for innovation. Memory and interconnects are very critical to AI hardware and AI processing, and they will continue to become more important in the future as our solutions get larger and as we want to process more data. There are some interesting and difficult challenges for improving memory and interconnect performance in order to meet the future needs of these systems. And they're really revolve around things like providing more bandwidth, providing better power efficiency, and in the case of memory, really providing more memory capacity as well to meet the needs of the larger models and training sets. But in the end, it's a really exciting time to be in the semiconductor industry. There's a lot more interest now, and it's really generated quite a lot of buzz and reinvigorated our industry in many ways. There's a lot of new opportunities and a lot of new technologies being developed, especially around domain-specific silicon. And there's some interesting and critical architectural questions that have to be addressed. So it is a fun time again, and memory and links are center stage in all of that. It's just a tremendous time to do some new innovation. So thanks very much for your time.